Okay. So what we have been doing is we have been the thing which you have the route which you have adopted till now is to consider only the thermal pressure and not the this one the and not the radiation pressure. Okay. Yeah. Yeah. Now in stellar interior, we have one which is the gas pressure, then two for any non-zero temperature, there is always radiation with radiation density equal to A T power 4 and pressure of radiation equal to 1 by 3 T power 4, A T power 4. Is this okay?
Yeah.
Yeah, okay. So, and this gas pressure, I will call it as PG. Okay. So the total pressure P is equal to PG. Sorry, in the notes I am calling it thermal. So we call it thermal because the origin is thermal. Thermal plus P radiation. Okay. Now I will do the following. I will say that my system consists of matter with the mean molecular weight is equal to mu. And as usual, I will call MP as the mass of proton. Okay. And I will call T as a temperature. Now, what is assumed is that the gas and the radiation are in equilibrium. So, we do not have T gas and T radiation. We have a single T which is same for both. Okay, that's because it is in equilibrium. And I have rho as the density of gas. Okay. So now, assuming that, assume gas is ideal, and hence I have Pg is equal to rho. When I say rho, it is assumed that this is a gas density rho. So I need not put rho g. Rho into kT divided by mu mp. You remember this formula, right?
Yes.
Okay. Now I say let beta be the pressure fraction of gas. And so I have beta is equal to Pg by the total pressure, and hence 1 minus beta is equal to P radiation by total pressure. Okay?
Yes.
Right? And now I will write this as now beta is equal to rho kT by mu mp into the pressure. And from here, I get that the temperature will be equal to beta, the total pressure, divided by Boltzmann constant into the gas density times mu mp. So this is the temperature in terms of the for this gas pressure. Okay. And similarly, I will have 1 minus beta will be equal to 1 by 3 AT power 4 divided by the total pressure. Okay. And now what I do is I substitute for this temperature because the gas temperature and radiation temperature are the same. I can write this as 1 minus beta is equal to 1 by 3 A beta to the power 4 P to the power 4 mu to the power 4 MP to the power 4 divided by the Boltzmann constant to the power 4 times P. And then I can simplify this to get P cube is equal to K by mu MP to the power, just rearranging of terms, to the power 4, 3 by A, 1 minus beta by beta, the whole thing to the power 1 by 3 times rho power 1 by 3. I mean, this is something which you just, I mean, you can understand this, right? I mean, I just calculate the temperature from here, substitute this temperature over here. That is why all this beta, P, everything has got a power of 4 because of this 4. Then there is a P here, which is which will cancel with this P4 and make it P cube, and that's how we get it. And this implies, oh, sorry. I mean, I'm just skipping step. Sorry. This one. And so P is equal to what I just now wrote. All right? Is it okay? Hello?
Yeah.
Okay. Now here, there is one thing which you need to understand. You see this density which is there, it is actually the density of gas and technically also the density of radiation. Okay? So density is equal to density of gas plus density of radiation. Now, the density of gas, even the rest mass is mainly dominated by the rest mass of the gas. Whereas, so, okay, so roughly we can write as the total density
This,
yeah,
in the above expression P cube, I think there is a factor of 4 beta.
you're
Yeah, beta power
absolutely
4.
right. Absolutely right. Yeah, this beta power 4. Very crucial. Okay. Fine. Thanks. Okay. Now the total density is equal to rho of gas plus rho of radiation. Now rho of gas is equal to rho the rest mass of gas plus the kinetic energy of gas plus rho of radiation. Now, whereas when you say pressure of gas, pressure of gas is only P of kinetic energy. There is no pressure from rest mass. And so, if my I mean, since my molecules are non-relativistic, this will be very small compared to this. And the radiation density will also be very small compared to this. So the rho will be dominated only by the rest mass density of gas. Whereas pressure will have both the kinetic energy term as well as the radiation density term, which may be of the same order in very high mass stars. Is the logic?
Can you repeat that again?
Okay. So, you may wonder, in pressure, I have said that this is pressure of gas plus pressure of radiation. Whereas here, I am just saying density of gas. Okay. And the reason for this is the following. When you have a high temperature, see, because since pressure of gas is purely because of kinetic energy of gas particles, by having high temperature, I can make these of the same order. So I have to consider both. Whereas in the case of density of gas, it is dominated by the rest mass density of gas, which far dominates anything about radiation and kinetic energy.
All right, got it.
Is it clear, other people?
Yes, yes.
Okay.
Sage, I'm not able to get that. Can you repeat it?
Okay. So, you may wonder about the following. Just a minute. You may wonder that while writing the density, I have said only density of gas. Whereas for pressure, I have got both gas and radiation. Now, technically, you should say this plus the density of radiation. Right? So, suppose we say this. Now, what does the gas pressure consist of? It is rest mass energy of gas, plus the kinetic energy of gas plus rho of radiation, right? Who was that? Just Snigdha.
Sujana.
Huh?
Hello.
Huh?
Sujana Sage.
Sujana. Huh? So you understand that the gas density consists of rest mass and kinetic energy.
Yeah, yes.
Right? So technically you should put both. But what happens is there is nothing like the pressure due to the rest mass of gas. But the pressure of gas comes from kinetic energy. And pressure of radiation comes from 1/3 the rho radiation. So in the density expression, there is a dominant term here which dominates over these two, so I neglect this. Whereas there is no such thing in pressure. So the pressure, you have to consider both gas and radiation, whereas in density, you can consider only the rest mass density of gas. Okay, so what I'm saying is gas is non-relativistic. And so rho kinetic energy of gas is much less than the rest mass energy of gas. Also, the radiation density, although may be of the same order as kinetic energy, but it is still much less than the rest mass energy of the gas. And hence, rho Ke gas and rho radiation can be neglected compared to rho rest mass of gas. Is this logic clear?
Yes.
Sujana?
Yes, Sage, it's clear.
Okay. On the other hand, in the case of pressure, both gas and radiation of this can be of the same order. See, here I am not neglecting radiation with respect to kinetic energy. I am neglecting each of these with respect to rest mass. But there is nothing like corresponding to rest mass. There is nothing in pressure. So there is nothing to neglect. So the pressure is only due to these two components. Is that okay?
Yes.
Okay, fine. So that is what we have. And right. Now, I can now ask the following. What about the central pressure? And the reason is, if you remember, when we were doing order of magnitude bounds on pressure, we had a bound on what is the pressure of the gas at the center, right? Total pressure at the center we had. Remember? The Milne bound and the Chandrasekhar bound and so on.
Yeah.
Yeah.
Hmm? we will be using that. So we want to calculate the pressure at the center PC. So I calculate everything at the center. So I have PC is equal to K by mu MP. But now, depending on the temperature, the material may be ionized in a different way at the periphery than at the center. So it means the mean molecular weight can also change throughout the star. So here, since we are looking at the pressure at the center, what I need is the mean molecular weight at the center mu c to the power 4 times 3 by A 1 minus the pressure fraction at the center. Are you with me?
Yes.
This to the power 1 by 3 times density at the center by 4 by 3. So this is the central pressure when you have the pressure due to both gas and radiation. Okay, just for this one. So the beta C is equal to pressure of gas at the center by total pressure at the center, and 1 minus beta C is equal to pressure of radiation at the center divided by total pressure at the center. Okay. We have seen earlier the bounds on pressure on PC. And that was, I had pi by 6 to the power 1 by 3 G M 2 by 3 rho C 4 by 3 less than or equal to PC, I mean greater than or equal to, and then greater than or equal to 3 by 8 pi Gm square by R4. You remember this thing? See, when calculating the pressure, we had various things and we also calculated, see, we got the pressure is greater than this, but we also got a pressure which is less than this amount. I hope you recall that.
Yes, sir.
Okay. So now we will use this inequality. And so I have pi by 6 by 1 by 2 power 1 by 3 Gm 2 by 3 rho C 4 by 3 greater than or equal to K by mu C MP 4 3 by A 1 minus beta C by beta C to the power 4 to the power 1 by 3 rho C 4 by 3. So you see something very interesting here.
The pressure ratio being bound.
This cancels out. It's exactly the same factor of rho C. And so you can have a direct relationship between the pressure fraction of gas at the center with the total mass of the star. Do you get it?
Yes.
Yeah.
You know, this is a very important result. So I have M, the mass of the star is greater than or equal to 6 by pi G cube square root K by mu C MP to the power 4, of course, 3 by A 1 minus beta C by beta C to the power 4 1 half. So you see the beauty of it, you know. You see, there, you know, the pi is 6 are numbers, G is a fundamental constant, mu C depends on the state of ionization, which is of the order of 1 anyway. MP is a fundamental constant, A is a fundamental constant. So it's a pretty neat relationship which tells you, I mean, if suppose the pressure fraction if is beta c, then the total mass of the star has to be greater than this amount if the star has to be stable. Otherwise, the radiation pressure and all will be so large that the star will be disrupted. Is this clear?
Yes.
Okay. Now, this is a very, very strong result actually. Because it tells you if you just know the pressure, the gas fraction of pressure, I mean, how much is the pressure fraction of gas, and you know mu c, I can tell you what is the lower bound on the mass of the star. Okay. Now, we go something further. We define a new quantity. We define a quantity define a quantity which is like the critical beta. Which is defined as m is equal to 6 by pi g cube square root k by mu c mp 4 3 by a 1 minus beta star by beta star 4 to the power 1 by 2. Basically, it is telling that what is the beta star is the value of beta c for which this inequality becomes an equality. Okay, so that's why it's the critical number. Is that okay?
Yes.
Okay. Now, so we need to see if we vary beta, very interesting result will be there. What happens to, how does this behave? So let us try to get, okay. So let me have an aside on behavior of 1 minus beta c by beta c to the power 4. Okay. So consider the function y is equal to 1 minus x to the power x by 4. Basically, x plays the role of beta and y is this whole expression. And we plot this. So first of all, what we find is, you know that x is a fraction, implies 0 is less than or equal to x is less than or equal to 1. So the range of x is 0 to 1. Okay. And now
Yes.
what I do is, let me see the behavior of this. So when x is equal to 0, so when x is equal to 0, then y tends to infinity. When x is equal to 1, y tends to 0, equal to 0. Okay. Let us now see the behavior of dy by dx. This will be equal to, if you just calculate, you will get 4 by x5 minus, no, plus 3 by x4. Okay. And d2y by dx square will be equal to 20 by x6 minus 12 by x5. Okay. Why am I doing this? Let us see how these things behave. First of all, I want to know, is there, okay, so let us first consider dy by dx. Now, dy by dx suppose they make it 0, will imply 4 by x5 equal to 3 by x4, which implies x equal to 4 by 3. Is it okay? Is that okay?
Yes.
Hello? It is not okay, because x has to be between 0 and 1. So the differentiation is okay. So what it means is, now this is greater than 1, and this implies at no value of x between 0 and 1, dy by dx is 0. So it does not have a minimum or a maximum. It is a monotonic function. Implies y is a monotonic function of x. Is that okay?
Yes, sir.
Yes.
Okay. Further, dy by dx, okay, is always less than 0. Okay, so if you take here, for example, if I take x equal to 0, then this will be minus infinity. Okay. And as you keep increasing this one, you will find that this is always less than 0. So both these together imply dy by dx is monotonically decreasing. Okay. Further, d2y by dx square, which is equal to 20 by x6 minus 12 by x5, is always greater than 0. Okay. Will always be greater than 0. Now, what does all this tell you? It has to be decreasing, but the slope has to be increasing, which means that the graph will be something like this. Is this clear?
Yeah.
Okay. What about others?
Yes.
Soundarya, Yaril?
Yes, Sesh.
Okay. Sujana?
Yes.
Okay. Okay. So, so all this I did just to show that it's monotonically decreasing, which implies that 1 minus beta c by beta c to the power 4 is a monotonically decreasing function of beta c, which is concave upwards. So without having to actually plot it, we know generally what happens to this. Okay. Just a minute. Actually, yesterday I sat down and plotted this entire thing. So let me see if I can. Now I'll be sharing these notes which are on the right hand side. Yeah. So you see this? What is this? Why is not only one of them coming? Strange. Okay. So you see the right hand side. Now this. Oh, you see the graph here.
Yeah.
Okay. Now I'll describe, but this blue line, black line which is there is actually this curve which is there. Now, what I can now say is, hey, wait a minute. Are you able to see the original one?
Yes. Meaning the one you're writing on, right?
This, okay. Wait a minute. This is something funny. Okay, just a minute. Okay. Now it's there. Okay. Fine. Yeah. Okay. So here, this black line is the graph. So it is sort of decreasing with concave upwards. Now I have defined something called beta star, right? Over here. I said, here. Where did I? No, just a moment. Here. This one. Okay. So now in principle, what I can do is I can actually take this and write, oh, sorry. And write beta star as a function of mass and mu c, right? Because all the other things which are involved here are just fundamental constants. 6, pi, g, k, mp, 3a, and 1. So it depends only on mass and the mean molecular weight at the center. And now what I'll do is I will draw this graph of 1. Okay, I will remove this now. Okay. I will draw this graph of 1 minus beta c by beta c4 versus beta c and say this is 1. So the allowed reach, so the graph was something like this. Okay. Now for a given mass and mu c, I can actually say I have this beta star. Is it all right?
Yes.
Okay. And now what I do is I draw a straight line over here, vertical line. So, okay, if I draw a straight line, then this quantity out here is nothing else but 1 minus beta star by beta star to the power 4. Is it okay?
Yes,
Yes.
yes.
Okay. Now it means if I go back to my mass here, it means that, so this is mass. So this quantity is nothing else but mass divided by all this, 6 by pi g cube square root, and then whatever k by mu c mp to the power 4, 3 by a, 1/3 or 1/2, or what is it? 1/2. Right? So this is what it is. Because I said mass in terms of the critical one. Now it means that if I say that the mass has to be greater than the some critical limit, then just a minute. Just a minute. Okay. Okay. So, yeah. If you are given a mass, then this quantity 1 minus beta c by beta c per 4 has to be less than that critical thing, right? Okay. Now, in the sense that with these two together, what I mean is 1 minus beta star by by beta star to the power 4 has to be less than 1 minus beta c by beta c to the power 4. See, because mass has to be, this is a very critical one. I substitute this on this side. I cancel all the terms. So 1 minus beta c by beta c power 4 should be less than 1 minus beta star by beta c star to the power 4.
Yes.
Okay.
Yeah.
Hey, does it sound okay, Soundarya? All the others?
Yeah.
Yes, Sesh.
Okay, fine. So it means my allowed region is this region. Okay, so this is that line, is this region. In this region, the only solution I am allowed is this. So it means that beta has to be greater than beta star. So it means that M greater than or equal to this thing 6 by pi g cube square root whatever k by mu c mp 4 3 by a 1 minus beta c by beta c 4 1 half implies that beta c has to be greater than beta star. Do you understand this? Graphically, this is how I have shown.
Yes.
Okay. So basically, I'm saying that I'm substituting M in terms of a critical quantity beta star, which I'm plotting here. And since this means that beta C has to be less than that beta star, this is the region which is allowed. And in this region, this is the only curve which is there. So it has to be beta C greater than beta star. The beta C greater than beta star. This implies that there is a lower bound on gas on pressure fraction of gas, and it also implies that there is an upper bound on the pressure fraction of radiation, because I have beta C greater than beta star implies 1 minus beta C is less than beta star, 1 minus beta star. Okay, and this is nothing else but P radiation divided by P, I mean, this is at the center, and this is P gas at the center by total state. You see this?
Yes.
Okay, I'll give some problems on calculating this further. So is this clear? I mean, this whole, I mean, I find this a very beautiful piece of, like working, of this whole thing, you see, actually the beauty about this whole thing is this formula, this formula, because, there are so many parameters which are there in the star, but it says that if I know the gas fraction and roughly the mean molecular weight, I can actually tell you that you can't have a star of a mass lesser than this amount. The
And
mass
Chase,
of the star.
we can, get a upper bound for the mass as well, right? When we know the central density and comparing the, lower bound of pressure, we'll get an upper bound for mass.
No, but that also has a mass term in it. No? You see, this thing has a mass here already. So it depends on mass. You see, central pressure is not something which you can control.
Yeah.
That's a derived quantity.
Yeah.
Okay. See, that depends on central density,
Yeah, that's what. Like, if I know the central density as well, then.
Yeah, that is of course there. That is of course there. I mean, that you don't have to go through all this, right? From this thing itself, Here itself.
Yeah.
Here itself, So that is not the point. But the beauty about this is that the lower bound of the mass of the star is completely determined by the pressure fraction of gas in the star. In other words, if the star, you see, when can radiation pressure become more and more dominant? When it is at a very high temperature. The problem happens that the pressure increases as pressure of gas increases linearly with temperature, whereas the pressure of radiation increases as a power 4. So as the temperature increases, the radiation thing climbs very fast. And that's why there is a bound. So the radiation can just disrupt the star. If it is very, I mean, if it's a, yeah, because there are two things which are happening. One is because, you see, mass is playing dual role. One, mass is causing gravity. But it, because of gravity, it is also leading to a high pressure, high temperature, which is trying to disrupt it. So it is a competition between these two. Is that okay?
Yeah.
Yes.
Okay. So this sort of brings this thing about the role of radiation pressure in stellar interior to a conclusion. I mean, this is a small module. Okay, I will give some problems and then it will be good to practice. The thing which I will next go is the important thing on heat transfer of stars. That's hardcore astrophysics. And I will talk today on the transport of heat because of convection. Okay, so since it's another topic, so we can just take a 5-minute break and then we can come back. Is it okay?
Yeah.
Let's now go to convection. Okay, let me. Yeah. Heat transfer in stars. Okay. Now let us say types of heat transfer. One is conductive transport. And here it is mainly relevant in solids. Okay. And not in the case of stellar physics and most astrophysical scenarios. This thing will, maybe it is relevant for the interior of, planets, not atmosphere, but inside the core and so on. There may, but not otherwise. The next thing is radiative. Now, transport via photons. Okay. Now, this is relevant in most astrophysical situations. And the third thing is convective. Here, heat transport through transport of hot fluid to the region of cold fluid. So here there is actually a matter transport. Okay. Now, when does it happen? Relevant when material is highly opaque. So, radiation cannot cannot transport heat. Heat gets collected till fluid moves carrying the heat. Uh, is this okay?
Yes.
Okay. Now, here in our case, we are concerned with 2 and 3 in these lectures. And first, we will see 3, which is convective transport. Okay. And now the interesting thing is basic physics of convective transport applicable not just in astrophysics, but also planetary atmosphere. Because, in fact, I will actually tell you about the whole physics of why there is pollution in Delhi in the winter. It all is related with this. Okay. So it has to do basically with the process of convection and the interplay of the temperature stratification and so on. Okay. So let's start this topic. The system I set up is as follows. I have at a certain height Z0, I have the atmosphere where I call the pressure is PO. I'll tell you why I call it O. Density is rho O and temperature is TO. And now here I am considering a blob of gas in which the pressure inside is Pi, the density is rho I, and the temperature is Ti. Now, initially all these will be same, but that will come to next. Now, the convective transport involves the following. Suppose I transport this blob for some reason in the vertical direction. This will be the blob here. I say that the pressure inside is Pi prime, the density is rho I prime, temperature is Ti prime, and at this height, which is Z0 plus delta Z, the pressure outside is Po prime, density is rho O prime, and temperature is To prime. and this distance is delta Z. Is the description of the system clear?
Yes, sir.
Okay. Fine. So you understand this PI way. Okay. Now, what we will be doing is the following. Now, if that blob, you see, suppose the pressure, temperature, and density of the blob inside and outside is the same at, say, Z naught, at Z equal to Z naught. That is at the ground level. And because of some perturbation, suppose one spherical region is moved up. Now, the spherical region itself will expand or contract, and depending on how efficient the heat transport is, it will be an adiabatic compression or an isothermal compression or something in between. Okay. Like, for example, if suppose there is no heat, I mean, when it moves, suppose there is no heat exchange, then if I move up, then when there is a lesser pressure, it will expand, but the expansion will be by an adiabatic process. On the other hand, if the temperature, if the heat exchange with the surroundings is very efficient, then it will be an isothermal process. Is this clear?
Yes.
Yeah. Okay. So what I am trying to say is that it is the basic heat transfer mechanism of the blob to the surrounding will determine what will be the pressure, density, and temperature at a height Z naught plus delta Z. Now, if at the new height delta Z, Z naught plus Z, suppose the density inside, which is rho I prime, is more than the density outside at that height, which is rho O prime, then it will settle down because it's a heavier fluid from the immediate surroundings. On the other hand, if in the new position rho I prime is less than rho O prime, then by buoyancy, it will be pushed even further. Is this clear?
Can you repeat it once?
So what I'm saying is, suppose that Z naught, I'm saying that Pi, okay, so at Z naught.
Yes, your video is turned off.
Pardon?
Your video. It'll help. We can see you.
Sorry, I didn't understand.
Your video is turned off.
Turned off, is it? That's
Yeah.
surprising. Oh, sorry. I didn't know.
Now it's
okay. Now you can see my beautiful face. Okay, fine. Okay.
Yeah.
Okay. So at Z equal to Z naught, let us assume that Pi is equal to Po, rho I equal to rho O, Ti equal to To. Okay. At Z equal to Z naught plus delta Z, Po has changed to Po prime, rho O has changed to rho O prime, To has changed to To prime, and depending on the thermodynamic process, Pi has changed to Pi prime, rho I has changed to rho I prime, and Ti has changed to Ti prime. Now, what is important is this change which is there outside is a given change for the given atmosphere. Whereas the change of pressure, density, and temperature inside the blob does not necessarily have to follow the same change as is outside. Okay. Depending on how much is the heat exchange and so on, it can chart its own course of history. Is this clear?
Yes.
Okay.
Yes.
Now, which means that in the new position, if okay, so in the new position, if rho I prime is less than rho O prime, it means density of blob less than density of surroundings. Okay. Then buoyancy will lead to upward motion. Okay. Is this all right?
Yes.
And this is what is convection. On the other hand, if rho I prime is greater than rho O prime, the perturbation returns the sorry, the blob returns to original position implies stable situation, implies no convection. That is, if it is like this, if suppose I have a hill and I have placed a ball on top. Now, if this, or for example, suppose it's like this, suppose I have a potential. Suppose I have a potential like this and keeps a ball on top, or if I have something like this and the ball on top, a perturbation will make it come back, so it is stable. On the other hand, if I have got a hill and I have a ball on top, a small perturbation will make it go away. It will be unstable. So convection is a situation of instability so that a small perturbation can make it go higher. Is that all right?
Yes.
Okay. And so we need to find out the condition under which this condition of rho I prime less than rho O prime is achieved. Okay. Now, before we proceed, we need to we need to study some time scales. Okay.
Sure. In your
Yeah.
the perturbation is given by changing its altitude, right?
Pardon?
Whether up or down. The perturbation is given by changing the altitude.
Yeah.
Okay.
So the question is, if I change the altitude, that is, it is to do with stability under like perturbation. If I perturb it, does it have a runaway situation? It's an unstable equilibrium or a stable
What comes
equilibrium
back?
that it comes back. If it is
Okay,
an unstable equilibrium, it is convection.
got it.
Okay. Fine. So now let us go ahead. Okay. So I will raises two things. Okay. When the blob rises, okay, the following things happen. Let us assume to begin with that, okay, so the system is such that I will say that, which is sort of I mean, this is sort of, reasonable, is that the pressure outside monotonically decreases with height. And this is, just recall that dP by dr is equal to minus G mr rho r by r square, and this is always less than 0. So it is monotonically decreases. Okay. So it means that PO prime is less than PO. Okay, so I will just for reference, I will get this here. Okay. And so PO prime is less than PO. And so what I say is, so it means that okay. So now let us assume that okay, so as so first, as inside pressure in general not equal to outside pressure at z naught plus delta z in the new position, the volume of the blob will change to come to pressure equilibrium with the surroundings. All right. You understand this, right? If the pressure is given, so it sort of expands. I mean, like if you have a balloon and it goes up in the atmosphere, as it goes up, it expands because outside pressure is less. So it expands to reach at pressure equilibrium. All right?
Yes.
Okay. Now, suppose tau mechanical is the time scale of attaining pressure equilibrium. In other words, suppose I change the pressure, how much time it takes to make it into a new equilibrium situation, and that is, I call it tau mechanical. And suppose tau dynamical is the time taken to move from z naught to z naught plus delta z. Okay. Now, if tau dynamical is much greater than tau mechanical, then it means that rate of motion is much lesser than the rate of attaining pressure equilibrium. Okay, is that fine?
Yes.
Yeah.
it means that as the blob moves, I can assume that at every position, pressure inside and outside is the same. Basically, it is like a quasi-equilibrium process. It moves so slow that at any time, it sort of expands to make it equal. So I can assume that there is a pressure equilibrium always. Is this clear?
Yes.
Okay.
Yes.
Okay. Sorry. Okay. Now, what this means is, I can say that the pressure, I already said, okay, we already we set Pi is equal to Po. This implies that further Pi prime is also equal to Po prime. That is, the pressure is always same inside and outside. Is that okay? It's all very, very important, all these steps. That's what I'm saying. It's all right now?
Yeah, yeah.
Okay.
Yes.
Now let us take another time scale. Okay. As the blob moves, volume changes, and in general, temperature changes. Okay. And hence it implies that the temperature inside may be more or less than the temperature outside in the new position. Okay. Now this implies possibility of heat transfer. If there's a colder object, is a hot object in a colder environment, it will lose heat. It's that kind of a thing. Okay. Now, one thing which you should remember is delta H is something which happens from the surface. So delta H will go as 4 pi r square, that is surface area. Whether the total amount of thermal energy inside is proportional to volume 4 pi by 3 r cube. It means that delta H by Q is proportional to 1 by R. It means that larger the R, more inefficient is the heat transfer because delta H is small. Is this clear?
I think it's better if you repeat it.
See, if you suppose you take a piece of metal which is in the form of a wire, and another in the form of a sphere, solid sphere, both having the same mass. You heat both of them to the same temperature. Which one will cool faster?
The one with more surface area.
More
I-
surface area. That is what I am saying. That's the heat transfer is proportional to surface area.
And what's that Q? I didn't
So
quite
Q
get
is
that.
the total, okay, Q is the total heat content in it. That depends
Okay,
on the
okay.
bulk. Right?
Got it.
Okay. So the delta H by H, so it means that larger the radius, more inefficient the heat transfer. Suppose tau thermal is the time scale of heat transfer. Then if my dynamical time scale, that is the time scale over which it moves up, if this dynamical time scale is much less than tau thermal, this will imply that heat transfer during motion may be neglected. Is that okay?
Yes, yes.
Okay. Now, if heat transfer is neglected, then what kind of a thermodynamic process it is?
Adiabatic.
Adiabatic. So it means it is an adiabatic process. Once it is an adiabatic process, now I know what is the relationship between pressure and density of the interior of the blob. What we will be the regime we will work is tau thermal is much less than tau dynamical, so that heat transfer is neglected. However, this is much less than tau mechanical, so that there is enough time for pressure equilibrium. So that is the time it takes to go up is large enough, sorry, am I got it wrong? Thermal is dynamical is, so dynamical is much less than thermal, is much less than thermal. So it means that it moves, okay, yeah. So that is, it moves fast enough that during the motion, there is not enough time for heat to transfer, but it is slow enough that the pressure equilibrium is maintained. So we are going to work in that regime. Is that okay?
Yes.
Okay. And this reminds me of an old advertisement of Amul milk chocolate.
I am too old for dolls, too young for the disco, but I think you're just right for Amul chocolate.
Amul chocolates, a gift for someone you love.
Okay. So, and the reason is the following. So it basically says that, so basically I'm saying that tau is the dynamical time scale is small enough than mechanical, the dynamical time scale is small enough compared to the mechanical time scale, but is large enough compared to the thermal time scale. So just like, it's too old for dolls and too small for disco. So I know it is too large for one, too small for the other, but it is the right regime for convective transport.
I think in here the science has to be changed.
Here, why?
Mechanical takes less time, which what we argued before.
No. Mechanical time scale is the time scale over which pressure equilibrium happens. Okay. Okay. I understand what you are saying. Okay. I'm sorry. So yeah. The right thing should be rate of thermal is much less than rate of dynamical rate is much less than rate at which mechanical equilibrium is attained, and that implies that tau thermal has to be much greater than thermalizing time has to be much greater than dynamical time scale is much greater than mechanical thing. Yeah.
Yes.
Yeah. So this is wrong. Okay. So now that we have set the regime where we are working, we will now proceed to say that the pressure equilibrium is maintained and an adiabatic expansion of the blob is there. Using this, we will calculate what happens to density at the new position and so. Okay, I think we'll stop with this. I think it's been heavy today, right?
Yes, we'll stop it.
Yep. Any questions? No questions. Unquestionable. Okay. Sujana, Saundarya, Snigdha, Hadia,
Yes, Sesh.
Harish,
Yes.
Yadil, everything is fine?
Yes.
Yes, yes.
Okay, fine. Okay, so see you later. Yeah, bye.
Thank you, Sesh.
Bye. Thank you.
Thank you, Sesh.
Thanks, bye.